Okay, welcome everyone again. So let me start today's class. Okay, so till now we have sorry, we had seen uh, the delay time definitions. Okay, so we had started this topic, and we had seen what are the various associated capacitances that we take into account, and then how do we combine all those capacitances, and we then connect a single lumped capacitance called as load capacitance at the output terminal of the inverter. Okay, remember this is a PMOS, this is NMOS. Okay, and both of the gates are connected to a single common input, and the common drain is connected to the output terminal. Okay, and all the capacitances are lumped into one single load capacitance here at the output terminal, and the source of the PMOS is connected to the power supply. Okay, and the source of the NMOS is connected to ground. Okay, and remember by default that the body of the NMOS will be connected to ground and the body of PMOS will be connected to power supply by default. So unless and otherwise it is stated. Okay, and at the input terminal we are feeding some signals. So since this will be a part of some digital signal, so the input signal will be in the form of streams of 1 and zeros. So sometime it will be 1, sometime it will be 0, and like that. Okay, and accordingly, since this is an inverter, the output will also be in terms of ones and zeros. Okay, so we had seen this, and remember one more thing, that since there is an output load capacitance connected at the output terminal. Okay, so the output will be assumed to be high when this capacitance gets charged up, and this will get charged up when this is connected to power supply via this path, via this PMOS, and this will be when this PMOS is conducting, that is when this PMOS is conducting, it will provide a conducting resistive path between the power supply and the ground and this load capacitance, and this will charge up this load capacitance. And we know that the operation is complementary in nature, so when PMOS is on, PMOS will be off at the same time. Okay, so there will be no connecting path between this terminal and this terminal. Okay, so the only path that will be available for the C load capacitance will be this one. Okay, and this power supply will charge up the load capacitance via this path. Okay, and when the input goes 1, okay, that will make NMOS conducting, and this path is now a kind of short circuit. Okay, and this path PMOS will get off, so this path will be open circuit. Okay, and under that condition, the charge present on the load capacitance will start to discharge via this path. Okay, so this will form a conducting a closed loop path, and that will help this load capacitance to discharge via this NMOS towards ground. Okay, and when it gets fully discharged, we call this as we call this as that the output is low, output becomes 0. Okay, so output becomes high or 1 when it gets charged via this path, and output becomes low or 0 when the load capacitance gets discharged via this NMOS. Okay, so remember this operation, at how the output load is getting charged and discharged, and the charging is taken as logic 1 and discharging is taken as a logic 0. Okay, and we had assumed that the input is this kind. Okay, and output is definitely is going to be inverted form of the input, so it takes some time to this is just discharging. Okay, and this is the charging of the load capacitance. So charging means it's going to be high and discharging means it's going to be low. So the discharging and charging takes some time. We call this as the propagation delay, and when it discharges from high to low, it is called as a propagation delay when output goes from high to low, tau PHL. Okay, and similarly when the output goes from low to high, this is termed as tau PLH, and this is measured with respect to the 50% level that is present in between VOH and VOL. Okay, so here considering this case, tau PHL will be the difference between T0 and T1. Okay, and similarly tau PLH will be the difference between T3 and T2. Okay, so this is tau PLH and this is tau PHL, and normally tau PHL and tau PLH are not of same value, they are of different values. Okay, they are of different values because charging and discharging does not happen by the same path, through the same path. They occur via different paths, and hence the values of these two propagation delays are not same, they are different. So we had seen these definitions, and now let us see how to calculate the delay time. So basically there are two methods to so there are two methods to calculate the delay times. Okay, calculate the delay times. So the first method is called as the average current method, and the second one will be the differential equation method. So let us start with the first method, that is the average current method. So as the name suggests that it will take into account something called as the average value of the current, average current method. Okay, and it is one of the simplest approach for calculating the propagation delay times, that is tau PHL and tau PLH. Okay, so what it does is we know that we know this relation Q is equal to I into T. Okay, so this can give us the value of T as Q by I, right, and we know that Q is equal to C into V by I. So this becomes basically equal to T. So we can use this relation sorry. So we can use this relation to find the value of time. Okay, and this is what is being used here. Look at here, the equation for tau PHL, that is propagation delay time when output goes from high to low. Okay, this is given as this, we can write from this equation C into delta V by I average HL. Okay, where C is the load capacitance, this is the load capacitance, and this delta V HL because here the output is going from high to low. Okay, I'm suffering from a bit of cough. Anyways, so output is going from high to low. Okay, so the change in output voltage when it goes from high to low, that is delta VHL. And the average current that flows between these two conditions, that is I average between H and L. Okay, so let us continue. So we were here at this equation, at this relation, C load delta VHL by I average HL. Okay, and C load delta VHL is the difference when output is going from high to low. So if we can go to this where is the diagram? Yeah, look at here. Output is going from high to low. So basically this is the peak point. Okay, this is VOH. Okay, and when it goes from high to low following this path, okay, and this is the value, the 50% value here. Okay. So this complete duration is the tau PHL duration. Okay, but there is a transition in the mode of operation of NMOS, because this output is going from high to low. So basically it means that the load capacitance is is discharging. So it is losing its charge, and it is losing its charge following this path, okay, like this, and it means that the NMOS is on, this is operating. Okay, and what happens as the output values goes on decreasing, as the output value goes on decreasing, the mode of operation of this NMOS, okay, changes. So for some duration, for the duration between T0 and T1 dash. So from here T0 and T1 dash, it will be in saturation mode, and for the duration between T1 dash and T1, it will act in linear region of operation. Okay, so basically and we know that the current equation for these two region of operation is different. Okay, and what is the value? What is that transition state, transition point at which it changes state from saturation into linear is this value, and that is VOH minus VTN. Okay, so this is all about the conditioning provided by the value of threshold voltage. Okay, so this VTN is the threshold voltage of this N MOSFET. Okay, so when the output goes below this, falls below this level of VOH minus VTN, the transistor NMOS switches into linear region of operation. Okay, now you can verify this, that why it is when this is high VOH, why it is in saturation mode, and when this becomes lower below a certain value, why it goes into NMOS, why it goes into linear region of operation. Okay, because we know you know how to determine the region of operation of a particular MOSFET. Okay, okay, you know that VD sat is equal to VGS minus VTN. So using this relation, you can very well identify the region of operation of a particular NMOS. Okay, so basically what I am trying to say here is that the tau PHL consists of two particular time durations. One, when the N MOSFET is in linear region of operation, and the second when it goes into one when it is in saturation mode of operation, and the other when it is in linear region of operation. Okay. So okay, that thing is there, but here for this case tau PHL is basically for this approach we will not take those two things here. We can simply write here the delta VHL, that is delta VHL is VOH minus V 50%. Okay, look at here, delta VHL is the difference in the output voltage when it falls from the peak most value that is VOH to the value 50%. Okay, and because this is the mark that we had set earlier, that below 50% we will assume that the output is low, and above 50% we will assume that the output is high. So output is high only when it is up to 50%. So basically when it falls from the peak value to 50% mark, okay, that is for this whole time duration t0 to t1. This is the difference in the output voltage, and this is what is taken here, VOH minus 50%. Okay. So this is the equation for tau PHL, right? Tau PHL, and similarly we can write the equation for tau PLH, that is when output falls from low to high, when output goes from low to high, when output rises from low to high. Okay. So the equation will be same, C load into delta VLH this time by I average in this region when output rises from low to high. Okay. So this can be written as C load into, and okay. So for this case, tau PLH can be written as C load delta VLH is what, is this difference, that is V50% minus VOL. We can see here in this diagram. Look at here, when output is rising, follow this path, when output is rising here, it is rising from VOL mark to V50% mark. So, okay, so basically the difference is V50% minus VOL in the output voltage level. Okay, in the output voltage level. So that's why it's written here like that, V50% minus VOL by I average LH. Okay, and the value of load capacitance is known, V50% is known, VOL is known, and the parameter that is left here is this I average LH and I average HL. Okay, the average current that flows when output goes from low to high or high to low. Basically, look at here, that is the average value of the current when output goes from high to low is, we can find out this as the average value of the two peak currents. Okay, so for example here, look at here, when output falls from VOH to V50% here, so the value of current when output is at this point and the value of current when output is at this point. Okay, so finding out these two extreme currents and taking the average value of these two currents will give us an approximate value for the average value of current. Okay, so IC when input is VOH and output is VOH, okay, and plus the value of the current when output falls to 50%. Okay, so take the average of these two extreme currents and divide it by 2, and you will get the average value of these two. Similarly, when output is rising from VOL to V50%. Okay, so what is the value of current? Find out the value of current when output is at VOL, and find the value of current when output is at V50%. Okay, and take the average of these two values. Okay, similarly, when output is VOL, okay, plus when output is at 50%, take the average of these two currents, and you will get the average current for output going from low to high, like this. Okay. So this is how we can calculate the value of average currents, the value of average currents, value of average currents, that is this I I average HL and I average LH. Okay, and since these are simple relations and simple empirical relations, they will not give us a very accurate, not very accurate values. So this does not give us very accurate values of estimation, but for first hand comparison, it's enough. Okay, so because the formulas are simple, the formulas are simple. So and the calculation is quick, very easy, quick and easy. Okay, so it is sufficient, just sufficient for quick analysis. Okay, when you want to analyze a circuit, a CMOS inverter circuit, and very quickly, just to get an idea that how the things are happening inside, we can use this method. Okay, but remember one thing, that this will not give you a very quick, very accurate value of estimation. So when you are trying to use this value somewhere else in the circuit involving a large number of components, then there you may get into trouble, because you will not be able to find, you may not get the accurate value for the whole circuit. Okay, so wherever accuracy is required, do not use this, but wherever you know that you can go with some inaccurate values, but the only thing is that to understand the behavior of the circuit, in those cases you can use this simple delay time calculations. Okay, that is by this method, average current method. Okay, so there is one more method that gives us a more accurate value, that gives us a more accurate value, and that equation, that particular method is known as a differential equation method. So let us see how does this work, because we know that the application of differential equations are huge, the scope is huge, and this differential equation approach is used almost everywhere, wherever there is some kind of flow, some kind of change in some parameter, or in some process, some quantity, whatever it is. So wherever there is some kind of difference or in change in values, you can use this differential equation approach. Okay, so let us see. Let us go with the calculation of the first parameter, that is tau PHL. Okay, that is the propagation delay time when output falls from high to low. Okay, so this propagation delay times can be found more accurately by solving the state equation of the output node in the time domain. Okay, so and we are working for tau PHL, that is output is falling from high to low. Okay, and we know that since output is having some one load capacitance connected, and it will discharge when it is fully charged, the output is high, when it discharges it goes low. So, and we know that the discharging occurs via NMOS. When NMOS becomes on, so there is a path available for this load capacitance to discharge via this path through this into this ground, and closed path is available for the current or the charge to flow. Okay, like this. So again the same illustration here, that output is going from high to low. It means that the input is going from low to high, because this is an inverter basically. So when input goes from low to high, the output goes from high to low. And as I had said earlier, that during this transition from this VOH to V50%, the region of operation for this NMOS will change. First it will remain in saturation mode for some duration of time, and then it will go into linear region of operation for some duration of time. So let us say that, so between T0 and T1 dash, this is in saturation mode, and from T1 dash to T1, this is in linear mode of operation. Which one? That is this N MOSFET. Okay, and this is the point, this is the level that will decide the boundary between these two regions. That this is the transition point, and the value of this transition point is this VOH minus VTN, where VTN is the threshold value of this NMOS inverter. Okay, V50%, we know that the 50% level mark, and VOH is the highest voltage level at output side. Okay, so basically, so this combination of this T0 to T1 dash and T1 dash to T1 will give us the complete value for this tau PHL. Okay, so this whole calculation will be divided into two parts. Okay, the first part involves when the NMOS is in saturation, and in this case we will use the ID SAT value, because in saturation we know that the drain current is basically different, and when it is in linear region, what is the value of drain current flowing through it is different. Okay, so and look at this equation. How do we get this equation? If you can remember that IC is equal to IDP minus IDN. Just very quickly, if I can draw, this is input voltage, this is output, and this is the load capacitance, this is VDD, and IDP is the drain current flowing through the P MOSFET, IDN is the drain current flowing through the N MOSFET, and if you remember, this was the value of IC, the current that is flowing into the load capacitance, IC. Okay, when you apply KCL at this node, you will get that IC is equal to nothing but IDP minus IDN, right? And this is what this equation is here. That is IC. We also know that I is equal to C dV by dt. So apply this formula here. IC becomes C load dV out by dt. Which voltage we are taking into account? This particular voltage, V0 or V output. Okay, so apply KCL here. You will get this equation, and first we consider the rising input case for a CMOS inverter. Okay, rising, RISING, rising input case. So that will make NMOS is on, and the load capacitance will start to discharge. Okay, and under this condition PMOS is off. So basically this is not working and this is on, this is off, and this is on. Okay, so only this part of the circuit is in action now, the lower part, the pull down network. Okay, so in this case the approximate value of IDP will be equal to 0, and when you put this value 0 here, it becomes 0, right? And we can write that C load dV out by dt becomes equals to minus IDN, okay. And in this case we know that this drain current will be the saturation drain current, because the NMOS is operating in saturation mode. So use the saturation drain equation. Okay, that is Kn by 2 Vin minus Vtn whole square. Kn by 2, what is Vin? The input value is VOH. Okay, and this is the threshold value for N MOSFET. Okay, and for this region it is applicable, because we had just seen in the graph. Just try to recall that thing. Okay, and we can use this simple relation this simple relation. Okay, and this particular value for IDN to formulate this integral for dt, that is minus C load integral 1 by IDN dV out. Okay, here the variable is dt. dt, remember, in this case we are taking NMOS to be in saturation for this case. Okay, and the dt will range from T0 to T1. Okay, so T1 dash, sorry. So the limit values for dt becomes T0 to T1 dash. Okay, and the value of V out falls from VOH to VOH minus VTN. Okay, and put up the value for IDN from this equation here, and you will get this particular equation. Solve this integral, solve this equation, and we'll get the value for T1 dash minus T0 as 2 C load VTN by Kn VOH minus VTN whole square, this particular equation. Okay, where the C load is the load capacitance, VTN is the threshold capacitance for N MOSFET, Kn is known, okay, VOH is known, VTN is again known. So all the parameters are known here, right? So the first part of the time duration when NMOS is in saturation comes out to be like this. Okay. Now the second second part, when output goes below this VOH minus VTN. Okay, in this region we know that the transistor will be in linear region of operation, and we will use the equation, the linear drain current equation, which is nothing but Kn by 2 2 V minus Vtn into V out minus V out whole square. Okay, this is actually VDS. V out is equal to VDS in this case, so VDS is being replaced by V out here. Okay, and Vin, we know that Vin is VOH, so replace Vin by VOH, it becomes Kn by 2 into 2 VOH minus VTN into V out minus V out whole square for this region. Okay, again use that equation, use that integral equation here, this one. The time will this time range from T1 dash to T1, and the value of V out will change from VOH minus VTN to 50%. Okay, these two things will differ this time, and the IDN will be the value of the drain current when it is in saturation, that is this particular value. You put up this value here and you will get this equation. Solve this equation to get the value of T1 minus T1 dash, and this will come out to be like this, minus 2 C load by Kn 1 by 2 VOH minus VTN log of V out by 2 VOH minus VTN minus V out. Okay, so again rearrange these. This will come out to be C load by Kn VOH minus VTN. Bring this minus negative sign inside this log. It will become something like this, log of 2 VOH minus VTN minus V50% by V50%, like this. Okay. So we have got the equation for both time duration, that is from T0 to T1 dash and T0 to T1 dash, and from T1 dash to T1. So combine this one with this one to get the complete tau PHL. Okay, and when you add this equation with this equation, okay, you will get the final value of tau PHL as this one. That is tau PHL. Tau PHL is C load by Kn VDD minus VTN. Common factor comes out. Okay, inside brackets we have 2 VTN by VDD minus VTN plus log of 4 VDD minus VTN by VDD minus 1. Okay. So this is the final equation for tau p h l using differential equation approach. And if you see, this is also not very complicated derivation. This is also simple, straightforward derivation. But the equation is a bit longer. Okay, that that will definitely take more time to calculate. Okay, and there are more parameters here. There are more terms here. Okay, there is a log term here also that needs to be calculated. So, okay, so this will take somewhat more time to calculate, okay, but the results will be more accurate. Okay, so more accurate as compared to the previous method of average current method. Okay, so this is the equation for tau p h l. Remember, tau p h l when output is falling from high to low. Okay, similarly we can find out the value for tau p l h. Okay, and you may expect some kind of similar equation as that of this one. Maybe, may not be. So we will see that thing. Okay, so this is an example taken from the CAG, example number 6.1. Okay, and it says that the VDD is power supply is 3.3 voltage. Okay, and VGS is 3.3 voltage. And when VGS is 3.3 voltage, the drain current reaches its saturation level, that is ID sat is 2 milliampere for VDS greater than equal to 2.5 voltage. Okay, so for this case VD sat is equal to 2.5 voltage, because above this value the current goes into saturation. So this is the value of VD sat, and this is also, we know that VD sat is equal to VGS minus VTN. Okay, so VGS minus VTN is equal to 2.5. So from this case, VGS is given 3.3 voltage. This is 2.5 voltage. You can find out the value for VTN as around 0.8 voltage. That is, the threshold voltage comes out to be around 0.8 voltage. Okay, so it says that the load capacitance is around 300 femtofarad and calculate the delay time necessary for the output to fall from its initial value of this to this. Okay, this is the 50% mark, and this is the VOH. This is VOH. This is 50%. Okay. So basically, it is asking us to calculate the value of tau p h l. So use that same formula that we had just seen in the derivation of. Okay. So remember this equation. Okay. When it was in saturation, this equation comes out to be like this. The saturation current is given to 2 milliampere. Look at here. This will help us in finding out the value of Kn. The value of Kn. Okay, this will come out to be something. So from this equation, you can find out the value of Kn. Okay, and then again it will be a combination of two parts. Okay, when the NMOS is in saturation. Okay, so it goes from VOH to VOH minus VTN, that is 3.3 to 2.5, and this will come out to be around 120 picoseconds. Okay, and from that previous equation you can find out the value of Kn to be around this much, and the second part, that is when it goes from saturation to 50% mark. Okay, that part will come out to be around 133 picoseconds. So the total delay will be the combination of 120 plus 133, that is around 253 picoseconds, like this. Okay. So straightforward application of the formula to calculate tau PHL, that is noted here as tau delay. Okay. Similarly, I advise you to go through this example number 6.2 from the book Kang. Okay, you will get some more insight how to work on the examples using these formulas. Okay, so that was the case for tau PHL. Okay, similarly, you can go for calculating for deriving the equation for tau PLH, and finally it will come out to be like this: tau PLH. This is the common parameter, that is C load by Kp VDD minus mod of VTP. Okay, now in this case you know that PMOS will be on and NMOS will be off, because this is the output is going from low to high, that is output is charging, and the output charges when it is connected to the power supply, and when it is connected to power supply when PMOS is on. Okay, when PMOS is on, when PMOS is on, the load C load will get charged to VDD via this path, okay. And you can very well compare the value of tau P, the equation for tau PHL. The common parameter is C load by Kn VDD minus VTN and here the common parameter is C load by Kp this time, because this is for the P MOSFET, and VDD minus mod of VTP. So similar, the common term is similar when you compare. Okay, and inside we have two factors, two terms. One is mod of VTP by VDD minus mod of VTP plus log of 4 VDD minus mod of VTP by VDD minus 1. These two things, these two terms. Okay. And actually for most of the time you will not find the values are not the tau PHL and tau PLH will not, they will be of different values, but for some conditions, for some balanced propagation delay, we can make these delays to be equal under some conditions, and those conditions are, because if you compare the value of the equation for tau PLH and tau PHL, the equations are similar to each other. So by very straightforward we can say that under some conditions the value of tau PHL will be equal to value of tau PLH. If you compare these two equations, you will find that when VTN is equal to mod of VTP and when Kn becomes equal to Kp, okay, under these two conditions the value of tau PHL and tau PLH will be equal. Okay, that is the rise time and the fall time for the output, rise and fall delay times for the output signal is same, and we call this as a balanced propagation delay circuit. That is, the propagation delays are balanced. The high to low delay is same as the low to high delay. Okay. And also, because till now we had assumed that the input signal is a step input signal. Step input signal means it does not have a rise time or fall time. Okay, but we can have the input signals having some rise time and some finite fall time. Okay, so in that case the delay will definitely increase. Okay, so when input signals involves some rise and fall time, and how to calculate the output delay times. So in those cases the tau PHL for the actual practical signal will become equal to tau PHL square when for input signal plus one more term, that is tau r by 2 whole square under root. Okay, and similarly you can find out the value for tau PLH by this equation. So remember these two equations, that is this tau PLH and this tau PHL were derived under the assumption that the input signal is perfectly ideal in nature. That is, the input signal is of this kind. It is not having any sort of delay in the input signal, but when it involves some sort of delay like this, okay, so it is having some definite rise time and fall time. In that case, the delay will increase, and the delay will increase by this term tau r by 2 whole square plus that same tau PHL square and under root of these two some values. Okay, so this is how we can calculate again the actual tau PHL and actual tau PLH, or the practical tau PHL and practical tau PHL, when the rise and the fall time of the input signals are given. Else when it becomes 0, when rise time is 0, the input signal becomes ideal and this factor becomes 0, and tau PHL whole square root becomes equals to tau PHL simply. Again, when this tau f is 0, the whole term will be nothing but tau PLH. Okay, like this. So let us come to the next topic after this propagation delay calculations. The ring oscillator circuit. Okay, so a CMOS ring oscillator circuit. So ring will indicate that it's a kind of a closed loop circuit, okay, that is closed in nature. Oscillator means it will keep on oscillating under certain conditions, okay, and it is made by using CMOS circuits. So basically when you combine odd number of CMOS inverters, so this is inverter 1, this is inverter 2, this is inverter 3, and when they are combined back to back and the output of the last inverter is fed to the input of the first inverter, okay, so this becomes a kind of closed circuit. This is called as a CMOS ring oscillator circuit. So it will oscillate, it will keep on oscillating under certain conditions, it will not stop. So this thing you can compare with the already studied oscillator circuit in your analog circuits. Remember there, if you can remember, that oscillator circuits were used for generating sinusoidal signals of certain frequency under certain condition. Similar thing is done here. Okay, it will produce some oscillations of some particular frequency, and that will be used inside the chip, because the chip requires some sort of clock signals to operate on, okay, of certain frequency. So under some situations, this CMOS ring oscillator circuit is used to produce those pulse signals of certain frequency that can be used to drive other circuits. Okay, and this requires the connection of odd number of inverters in a cascaded fashion. The output of the last inverter is connected back to the input of the first inverter. So look at here, this is inverter number 1, this is the input of inverter 1, this is coming from the last inverter, that is V3. This V1 is the output of first inverter, that also forms the input of second inverter, and V2 is the output of second inverter, that also forms the input of third inverter. The inverter third has got output of V3 that is connected to the input of inverter number 1. Look at here, and at each of the output nodes of these inverters we will have a particular load capacitance. Let us call this as a load 1 for inverter 2, load C load 2 for inverter third, C load third. So basically this is a 3-stage ring oscillator circuit that consists of identical inverters connected in cascade manner. Okay, and when you plot the waveform for this ring circuit, let us say that this is the first inverter. Let's start from the first inverter, and let's say that inverter first is giving an output at V1 that is rising in nature, that is this particular inverter output V1 is rising, and this forms the input to V2, input to inverter number 2. So when V1 goes high, V2 should go low. Okay, so when V1 is high, V2 goes low like this, and when V2 goes low, V3 should become high. So V3 should become high. Right. When V3 goes high, V1 again should become low. Okay, right. And when V1 goes low, V2 goes high. V2 goes high. When V2 goes high, V3 goes low. V3 goes low. So in this fashion, you can we can draw the waveform for this particular ring circuit. Okay. And this is the value for VUH, this is VUL, and this is the 50% level. Okay, and remember, we can calculate also the value of the delay. So this is the delay between this point and this point. This is for V2. V2 is the output of inverter 2, and this is for V1, which is the input of inverter 2. Okay, so the difference between output and input for inverter 2 will be the delay value, the tau p HL, because the output, that is V2, is falling from high to low. So this becomes tau p HL for inverter number 2. Okay. Similarly, you can verify that this particular duration will be tau p LH3, because for third inverter, okay, the third inverter, the output is V3. The output is V3, which is actually rising from low to high. So this becomes tau p LH3. Similarly, this will be tau p HL1 and tau p LH2, tau p HL3 and tau p LH1, and one complete cycle is complete, one complete circle is complete, one complete path is here, and the combination of these all delay values will give us one time period, one complete time period for this oscillation that will be produced. Okay, so this is the time period of oscillation. And this will be the invert of the frequency of the oscillation. Okay, so look at here, what is an ring oscillator? Nothing but a cascaded connection of odd number of inverters with the output fed back to the input, right? The behavior is astable, that is the any node is not stable at any at times, they keep on changing the values. Okay, and this will oscillate once if any of the inverter input or output voltage deviates from the unstable operating point, that is VTH, and this VTH is the threshold voltage level for the inverter. Okay, remember, this is different from the threshold voltage of the devices. Okay, so what happens that each inverter triggers the next inverter, and similarly it keeps on going and the last inverter triggers the first inverter, right? So we had just seen for this 3-stage ring oscillator, the value of this time period for one oscillation will be the combination of all these 6 propagation delay times. Okay, that will be 6 tau p, and we can calculate the value of frequency by using this formula 1 by t, that is 1 by we can generalize this 2n tau p, okay, where n is the number of inverters. So here n is 3, so it becomes 3 into 2, 6. So 1 by 6 tau p. So remember, look at here, 1 by 6 tau p. So this is the general formula, okay, to calculate the frequency of a ring oscillator. So this was a small topic just to go through. Remember that these oscillators, these ring oscillators are used as to generate some sort of frequency signals within the chip, okay, but they does not provide a very high or very accurate signals or very stable signals, but for general purpose they can be used where the stability and accuracy is not of very high concern. Okay, so but for higher accuracy and stability of the frequency, off chip oscillators that are basically crystal oscillators are used, not the ring oscillators. Okay.